Just quickly, the main idea is quantum computers are very fragile today because they are not robust. It's very easy to disturb the state of some quantum system that's storing information and manipulating information, bits or quantum bits. So if you can store those quantum bits, the information, in topologically robust, topologically invariant, so properties, physical properties in physics that are topological in a sense, so that when you disturb them, those topologically invariant, meaning unchanging, those properties in effect are robust, they don't get disturbed. Now, to understand that, you need to know quantum field theory, you need to know topological quantum field theory, you need to know a lot of topology, homology, cohomology. It's advanced stuff, right? So you need to know a lot of pure mathematics, you need to know very high level mathematical physics. So I need to take you up to what I call PhD 2, meaning second year classes, theory classes at PhD level. So I need to take you up to up to that level. So you need to know not just a lot of pure math and theoretical physics, you also need to know a lot of computer theory, right? Because you'll be, if you take up a job in this, and believe me, in a couple of years, once topological quantum computers become a reality, and there's progress every month, once topological quantum computers are a reality, therefore quantum computers become robust, and then therefore scalable. We can build quantum computers with large numbers of qubits or quantum bits, and therefore computer science just gets revolutionized because quantum computers can outperform classical computers by a factor of 2 to the power n, where n is the number of qubits that you have in your quantum register. So a revolution. When computers become exponentially more powerful than today's classical computers, then everything changes. You could then simulate nature, which will just revolutionize the sciences, revolutionize technology, and 21st century technology will be based on it. And therefore, large numbers of people, very, very smart people, will need to be taught the basic principles of this technology, the science underlying the creation of topological quantum computers. And that's TQC, and hence you'll need to know graduate level, PhD level, pure math physics, and computer theory, right? Okay, so they're the next two topics. Now, let's talk about what I'll be doing. Now, it won't be immediate because it's taking me a month and a half or so per course. I'm noticing in practice. So let me now talk about the future courses in finite group theory and why, and like here are like 5 levels. So this is the text we've now just finished by Barnard. That was at junior senior level. Okay. Now at Masters 1 level, in fact it's a bit senior M1, it's a bit of both, but a substantial portion of it is definitely at M1, first year Masters level. The book is called A Course in Group Theory. It's by Humphreys, Oxford University Press. Right? This book is available on eMule if you want to get it for free. Right? That's at M1. At M2, the text I've chosen is by Kurzweil. I've shown you some of these before, not all of them. Right? Called The Theory of Finite Groups: An Introduction, and it's by Springer. And it too is available on eMule if you want to get it free, or if you prefer hard copy, then you pay for it. And at PhD 1, in other words first year level PhD, a book by Aschbacher called simply Finite Group Theory, published by Cambridge University Press. It is on eMule. you can get it for free if you want, or if you prefer hard copy, you pay for it. You can get it fairly cheaply on from, say, Amazon.com, secondhand if you want, right? And Ashbacher was one of the genii, one of the leading lights behind the classification of the simple groups. And I'm particularly keen on teaching you about simple groups because of its enormous importance. I've mentioned this several times during this lecture course. And a lot of that theory around the classification and the nature of simple groups themselves is contained in this text. So this is an important text. And again, now this is PhD 2 level, again by Ashbacher. And I only discovered that this was on email recently, so you may have trouble getting this one if you prefer to have it for free. And if you buy it, it's not cheap. But at PhD 2 level is a lot of discussion on the simple groups themselves. There are 26 exceptional simple groups, and some of them are just huge, just of enormous size. In fact, the biggest one, called the monster group, has its order is of the order of magnitude 10 to power 53. Right? So it's just humongous, right? So it's again by Ashbacher, and it's just simply called sporadic groups. That's what I just called the exceptional groups. So there are 26 of them, and the classification theorem proved that that's all there are. Yeah, there are 26 of them, and that's it. Well, there are a few other categories, but in terms of the sporadic groups, there are only 26, including the monster. So here's Cambridge University Press, published '94. It is available on email for free if you want to get it. So I've got it here in hard copy, right? And why all this emphasis on simple groups? It's because a growing number of theorists think that future physics, string theory and whatnot, will be using increasingly ideas, the mathematics coming from simple groups. It's still largely untapped. There are still a lot of mysteries from the point of view of the mathematicians about the properties of the monster group and other simple groups. So strong intuition that the future will play, that simple groups will play a major role in the future in the development of mathematical physics. Okay, so if you guys keep following me for years and years and become math physicists yourself, equally at home speaking the language of pure mathematics as mathematical physics and some computer theory, then we will see if I'm right. My strong gut feeling is that the simple groups will become a very important tool for the development of mathematical physics, string theory, the theory of everything. The big dream of string theory. Well, nowadays it's more replaced by, we don't talk about strings so much anymore, we talk about branes now, B-R-A-N-E, short for membrane, these multi-dimensional surfaces. But collectively still call it string theory. And I'll be teaching string theory. In fact, well, I mean, it's here, why don't I just mention it? The very first string theory course I'll be teaching at M1 level is, what's this one? This is the text, available free on email. So it's called A First Course in String Theory, and it's by Zwiebach, Z-W-I-E-B-A-C-H, Zwiebach. Okay. Now, this course was taught at undergrad level at MIT, Massachusetts Institute of Technology. Now, that pretty well means it's at master's level virtually anywhere else, unless it's Harvard or Caltech. Because to be an undergrad at MIT, you pretty well need a threshold IQ to get in of about 160, which puts you at genius level anyway, right? So I'll be teaching it at M1 level, and it's still fairly simplified because if you do full string theory, you need a powerful lot of math and physics, which is what I'm trying to teach, taking you up to M2 level. So I'll be teaching a lot of string theory later, in later years, that have to get there, right? I mean, you have to learn to crawl before you can walk, and you have to walk before you can run, and you have to run before you can fly, kind of thing. So step by step, and it's a fairly slow process because I have to go through all this stuff. All right, okay, so they're about the books and future courses. Now some general, I've written it down here, it's probably too small for you to see. These are just prompts, reminders for me, the topics I wanted to mention. I've written here the free professor impact, and the idea of grading centers. I'm curious, I'm very curious to see how long it will take, like how many years, before the sort of thing that I'm doing, and I'm calling this free proffing, right? I'm a free prof. I give these advanced lecture series at grad level for free. I consider it an abomination that parents have to pay $40,000, $50,000 per year for undergrad tuition at the top schools in America. That should be killed off. It's a huge waste, massive inefficiency. And now that it can be killed off, I think there's a moral obligation that it should be killed off, because we can do it now. I mean, the camcorder that I'm talking to costs a few $100s with a tripod, $50 whatever, and a whiteboard. It can be done now. So I appeal to other, especially retired professors around the world, especially native English speakers, because you speak the world language, to put your knowledge using a camcorder and uploading your wisdom, your knowledge, for the sake of the education of the world, and to do it for free, and to kill off this financial abomination of $40,000, $50,000 a year that keeps parents poor, and it's unnecessary. So I'm on a kind of ideological war against the teaching side of universities, and especially undergrad colleges. They should be just wiped out. But they need to be replaced by something, which I call grading centers. Now, as things are at the moment, this free proffing is my term. So I label myself a free prof. It's new, right? People don't quite yet know what to make of it, and its full impact has not yet been felt. I'm still waiting to see the first articles predicting what's going to happen. They're just a few intellectuals crying in the wilderness at the moment, talking about the probable impact of free proffing. And they probably don't even have a label for the phenomenon, what I call free proffing. So we will need universities to adapt themselves. Like if you have a research university which gives degrees, masters, PhD, that kind of thing, the research side will be kept. I mean, we still need, we need research, of course. So that will not die out. And people will come together, with face-to-face contacts for doing research, because brainstorming